welcome back to Introduction to Computer Networks. This is Polly speaking live again from NTU. And you guys are all welcome to come back. And hi, Yongyi, Amy, Zhuxun, and Lucas. Good morning to all of you. All right, so let's check out the announcements today, all right? So first, guys, exam is coming up again next week. Okay, so you want to take things easy, and all you need to do is to do your best. Okay, so maybe I can share a couple words about the exams. Yeah, it is necessary for the professors to tell you guys apart. Otherwise, you guys will all get A plus, right? It doesn't make sense. But it is also for you guys to see, okay, how you do, and whether this is the subject for you. Okay. So if you've been doing great, hey, good for you. Okay, this is certainly, computer network is certainly a subject that you can consider pursuing further. Okay, but if you did not do as well as you have expected, think, have you spent enough time on this? Whether you have time to invest more. If not, then take things easy. Okay, accept what the grades say, and so you know that by allocating the time you have now, it's not quite enough for the subject, and that means that this subject might not be exactly your thing, because it does take more time than what you have expected. Okay, so it is serving a purpose. The exam is also serving the purpose for you to know a little bit more about yourself. It's very easy that you confuse something that you'll be good at, which is called the aptitude, from your interest, things that attracts your attention. Okay, so these are actually different in many cases. All right, things, people you find interesting might not be a good fit to your personality, to how your brain works. Okay. So do observe more of yourself, okay? All right, so that's exam 2 coming up. Number 4, hey, it does look like we have a little bit more time. Okay, so Polly is actually adding one more quiz today. Okay, so this week we'll have 6 quizzes due, if I recall correctly. 5 or 6 quizzes due. Okay, let me make sure. 1, 2, 3, 4, 5, 6. Yeah, indeed, 6 quizzes due. Okay, this week, and we have completed them. We'll complete them all in class. Okay. Now, the topics today, and yeah, hi. More of you just popped in. Ting Xuan, Qing Ying, Cheng En, Yu Ji. Oh, Yu Ji, and Yu Ting. Okay, welcome and good morning. The topics today, okay, are gonna be in 3 groups. Okay, first is to finish description of TCP's condition control. We just started it yesterday. Okay, and there are more to come. The second set is to introduce the finite state machines of TCP's condition control mechanism. Okay, so it's concrete, and the rules are clear. And in the second part, we're going to introduce one more optimization to TCP, but on the condition control part of TCP. That is called the fast recovery. Okay, that is a big subject today. And the last group is the extra topics that might be interesting to you. Okay, which includes a version of TCP that does network assisted condition control, but that never get deployed, okay, into the real internet. You will see how it works then. So now the first set of topics, TCP's condition control. Okay, let's recall from yesterday. We see TCP in the steady state. Okay, the condition window size, which means the transmission rate. Okay, condition window size large, faster transmission rate, narrower, a slower sending rate. Okay, so what TCP does is just the trick is just to change the window size. Okay, because then that scales also the sending rate. So TCP's in steady state, the condition control is to do what? additive increase, so slowly, linearly increasing the window size. But when there's a loss detected, multiplicative decrease, suddenly cutting the window size to half. Okay, so this is what TCP does in the steady state. And you can probably understand halving the window size to half when the loss is detected, because the quiz yesterday, many of you probably have noticed that the best strategy to find the right price is to do what? Binary search. Because you close the step by half of the distance, by half of the margin that you're looking for the right solution, isn't it? So TCP there, hey, currently at this window, and there's minimum, right, in window size 1. So dropping it to half is to quickly find whether this is the lower bound. See? So that strategy, smart, multiplicative decrease, perfect. But what about additive increase? Right? The best strategy should be, now you know the original window size is not good because we have a congestion. And dropping it to half, in case the packet is coming through, egg is coming back, why don't we just jump the window size to be right in the middle of the original window and the half of the original window size? Why we slowly add the window size? Why? That is obviously not very smart, okay? But you know what? The point of the quiz yesterday is also to let you see, given 30 seconds, is that enough for you to find the right price? Not quite, isn't it? You see, the process of finding the right price, similarly for TCP, the process of finding the right available bandwidth, right window size, will also take time. Okay? And so such a jump from half to the full, you don't know whether you're going to create another congestion. So in TCP, this is steady state congestion control. So if you want TCP to stay in a steady state, instead of running into congestion, back down, and running to another congestion, back down, and running into another congestion, back down, then okay, slower, increase the window size slower. Okay, that makes TCP steady. Okay, and that is also the goal for TCP steady state. We want to keep TCP flow steady. Okay, so that explains why additive increase. Now, I keep saying that's TCP steady state. So is there another state in TCP that we can be more aggressive? You know what? Yes, there is a state in TCP that we do increase the window size aggressively. Okay, a little bit more like binary search. That is called the slow start state. Okay. Now, you might be thinking, hey, slow start sounds slow, but you said that we increase the window size aggressively. Yeah, they are counterintuitive. In this video, you will see in the first part, there's a reason we call initialization state of TCP slow start, because we always start from a small window size. That means the TCP at the beginning is always slow. So slow start is just to refer to TCP at the beginning, very slow. It's not to refer to the window size changing mechanism being slowly increasing. Okay? So in the second half of the video, you will see how aggressive we increase the window size, okay, in TCP's initialization state. And so that is slow starts congestion control, what this video is about. Something that's a little bit unusual in TCP's process of discovering the proper sending rate is this. There's an initialization phase, and the mechanism is called the slow start. Okay. What it does there is, when TCP is just starting, a connection is just starting, the initial window size is set to 1 MSS. And the increasing pace is no longer AIMD, it's actually what? Doubling the window size per round trip time. AIMD is what? Increasing the window size by 1 MSS per round trip time. Wow, so that's actually quite aggressive, isn't it? You are correct, because the window size in slow start, in the initialization phase, is going to increase exponentially. Because every round trip time, you double the size. Every round trip time, you double the size. As opposed to in AIMD, every round trip time, you increase by 1 segment size. Every round trip time, you increase 1 segment size. Right? So, yeah, the initial rate, very, very small one. So slow start is actually referring to, yeah, the initial window size being, yeah, the lowest possible. But the increasing rate is actually exponentially fast. Okay, so this is actually the part of design in TCP's condition control that can confuse you a little bit. It's slow start, but it's actually increasing really, really fast, right? So the intuition says this is fast start, in fact. Yes, you are correct, but the slow here actually meant the window size, the initial value, is a very low value. Okay. The last point I want to make is this. Okay. Doubling window size per round trip time in the implementation is actually done this way. Okay. Window size is incremented by 1 after receiving an act. Okay, so look at the illustration I have on the right. A is the sender, B is the receiver. A originally in slow start having a CWND of 1 MSS. That data packet will go, receiver here will send an ACK back. Host A here being the sender receiving an ACK will do what? CWND plus plus, and the increment is 1 MSS. As a result, it was originally 1, now 2. Therefore, sender here can send 2 segments in MSS. So these will go and generate 2x coming back. Sender here receiving 2x will be calling this line twice, therefore 2 will become 4. Similarly, 4x comes back here, and this will be called 4 times, therefore the window size becomes 8. And the next round, 16. You see an exponential increase here, right, by a factor of 2, isn't it? So overall, TCP's process of discovering the proper sending rate is more like this. This is a TCP connection, and this is the beginning of it, and this is the end of it. So there's this initialization phase where we run the slow start mechanism, okay, and the behavior of the window size is AIMD. And then in the steady phase, we run this congestion avoidance mechanism. The behavior of the window size is AIMD. All right, so EIMD, okay, in the initialization phase, and AIMD in the steady state phase. All right, and so EIMD makes sense because you quickly discover the upper bound. Okay, just like multiplicative decrease, you quickly discover the lower bound. Good. So I hope that explains the window size adjustment mechanism in TCP to do congestion control. Now we switch the topic a little bit, talking about the feedback, the losses. If you recall, TCP's reliable data transfer mechanism, how do we discover a loss? There are actually 2 ways, okay? Because there are actually 2 situations we retransmit packet. One is what? The retransmission timer times out. The other is what? Recall the fast retransmission mechanism. When we receive 3 duplicate acknowledgements, we also retransmit. So there are actually 2 ways to detect there's a packet loss. Timeout versus 3 duplicate ACKs. Okay? So in these 2 different loss cases, the window size is treated differently as well. Okay, so this is what this video is about. And you heard probably pollys saying, yeah, TCP increases the window size when there are no losses and decrease when there's a loss. But if you think a little bit carefully, in TCP, the sender detects a packet loss 2 ways. One is, yeah, there's a timer set when the packet is sent. When the timer expires, the sender there discovers the packet is lost and then retransmit. But in TCP, there's something also called fast retransmission. We are retransmitting packet faster right after receiving triple duplicate ACKs. So there are 2 ways in TCP sender to detect a packet loss. In fact, in TCP's congestion control, we are also adjusting the window size differently depending on which type of loss is being detected. First is, a loss being detected by sensing the timer timeout. We then set the window size all the way down to 1 segment, okay, and then grow exponentially just like in slow start state. After a certain threshold, then grow linearly just like in the congestion avoidance state. On the other hand, when the loss is detected by seeing 3 duplicate acts, then the congestion window is actually cut to only half the current window size, not all the way down to 1. And then grows simply linearly. So this is very much like what? AIMD. Yeah, you're actually right. When the loss is detected this way, the TCP sender is actually dropping the sending rate to half and then continue on with the AIMD, therefore, into the CA state, the congestion avoidance state. So the TCP connection here is still in the steady state. But if the loss is detected this way, it appears that the TCP thinks this is actually a more serious scenario. Therefore, the window size needs to go all the way down and then being reinitialized, okay, until the window size grow to a certain degree. Then we do the AIMD, like in the steady state. Okay. Now, based on your intuition, which loss of these two you think is more serious? Yeah, I know, it's quite obvious, right? Because in this case here below, at least you get to receive 3 duplicate acts. That indicates the network is still capable of sending 3 packets through. Therefore, you get 3 acts back. But this scenario here, it's top. You don't get any data through, you don't get any data back, or you get only 2 duplicate acts back. So, yeah, more serious. Therefore, okay, Windows drop down even more aggressively, all the way down to 1, and that's restart, reinitialize again. Now, the only thing that you thought, interesting is this. So we have not yet defined what is this threshold yet, because it seems that this threshold is there to determine how a TCP connection there start from the initial state, entering the steady state. So that is also the point to decide. When do we change the mechanism from slow start to congestion avoidance? First point to add to the slide is this. The threshold in TCP's implementation is called SS thresh. You guess, S and S here actually meant S and S here in slow start. Second point, the whole mechanism differentiating how we adjust the window size depending on the type of loss being detected is implemented in TCP Reno. Yeah, I know. TCP designers is a bit weird. They like to call different versions of TCP with names instead of using a number. So Reno there is essentially the version 4, TCP version 4. There's another version of TCP, TCP Tahoe. So this is actually the first generation. So what's being designed there is this. The loss, no matter whether it's detected by timeout or 3 duplicate acts, the window size is adjusted the same way, always down to 1. That means Tahoe there is very, very conservative. Whenever there is a loss detected, the sender always go down to the lowest rate possible. And that might be a bit too slow based on experience, therefore, in the second generation. The designers begin to say, hey, maybe in this easier case, okay, at least we see 3 data go and then 3 duplicate acts back. It's not so bad. Let's only cut the window size to half and then remain in the congestion avoidance phase. All right, so that video explains when the loss is discovered in 2 different ways, the window size will be treated differently. The last video is just to explain how the SS thresh you heard in the video is determined. So what I'm illustrating here is TCP Tahoe's window size changing over time. At the beginning, window size set to 1 segment. And then slow start, right? This is the initial phase. And therefore you see exponentially fast growth, the concave curve. And this is gonna go until we hit the slow start threshold. That's when we exit slow start and enter congestion avoidance, where we do AIMD, so additive increase. At this point, we detect a packet loss due to 3 duplicate acts. But in Tahoe, we just drop the window size back down to 1 again. And then slow start again, a concave curve, until we hit the threshold again, and then AIMD again in the condition avoidance state. Now, what's in Reno is, however, when we detect 3 duplicate acts, a packet loss, what we do is more simple, where we just reset the window size to half of the original window size, which is 12. So we set it to 6, and then continue to grow the window size AIMD, such as in the condition avoidance state. Okay. Now, by looking at this plot, you also see, hey, we are switching from the slow start to the condition avoidance state using the threshold. At the beginning, the SS thresh is initialized to a fixed value. But afterwards, you see, the SS thresh is also changing. And when we detect a loss, when we need to reset the condition window size down to some lower value, when that happens, when the packet loss is detected, the threshold here is also reset. And the value is set to exactly half of the window size before the packet loss is detected. So SS thresh is set to half of the window size just before the loss event. Okay. So in the TCP Reno's case, it's convenient. We set the threshold to the half of the window size, and we also set the window size to half of the earlier window size and continue to grow like this. So it's also saying passing the threshold and then this connection in the condition avoidance state. If we go back to the original question asking, when do we switch from the slow start state to the condition avoidance state, or from exponential increase back to linear increase? And so it's very clear. Once the condition window hits the SS thresh, the slow start threshold. Because if you look at this, slow start, passing the thresh, growing linearly. Slow start, passing the threshold, growing linearly. And in this case, we see 3 duplicate acts, therefore we drop the window size to half, and we drop the SS thresh also to half. But hey, as long as it's beyond the thresh, the window size grows linearly, then the design does not conflict, okay, with other parts of TCP's condition window adjustment mechanism. All right, now you see the SS thresh, there's an initial value, all right, but that value is adapted, okay, according to the window size, okay, whether there is a condition, okay. Whenever there's a loss detected, SS thresh is also dropped, okay, to half. The half of the window size at the time the loss is detected. Okay, so SS thresh is a dynamic variable. Okay. Now, before we go down to talk about the finite state machines, keep this in mind. TCP initialization state is also called the slow start state because the sending window size is very small, so it increases the window size aggressively, exponential increase. In steady state, it is also called the congestion avoidance state. The purpose is to avoid congestion. Okay? So the window size will increase conservatively, linearly. Okay, so EIMD at the slow start state, AIMD at the congestion avoidance state. You have the whole TCP's condition control mechanism. Now, let's draw the whole mechanism into finite state machine. Let's start with the easier component, the slow start. Okay. Now let's summarize TCP's condition control. And what I'm going to show you is actually a little bit more formal using a finite state machine. And you see how TCP sender here implements, okay, the mechanism of adjusting the window size. The full finite state machine has 2 states. Okay, each represents different phases of TCP's condition control in a connection. So the first is the initial phase, the slow start phase. The initialization transition here is actually initializing the condition window size to 1 segment, and then initializing the SS thresh to 64 kilobytes. I think this number could differ from operating system to operating system, and then initializing the duplicate ICANN. Alright, so that was clear. Let's move to the normal transitions. There are 4 of them. Okay. If you look a bit closer, the top 2 here are actually the transitions handled in the cases where the sender receives acts. The bottom 2 are the cases where the sender detects losses. This one here is actually detecting a loss due to receiving 3 duplicate acts. This transition here is actually detecting a loss due to timeout. Now let's talk about each of these transitions a bit more. So number 1 here is if we receive a new act. Now according to source star mechanism, the condition window needs to be incremented by 1 segment, and that's it. So duplicate act count is reduced to 0 just so to clear all the duplicate act counts, because now we are receiving a new act. So we should definitely clear the dupe act count. And at this point, then we employ the rest of descenders mechanism, the RDT part of it, so that we would slide the window over and then send new segments. And how much we send out there depends on the result of the condition control mechanism working. And next, transition number 2, this is when we receive a duplicate act. So what we do here, of course, increment the counter for duplicate act. And what do? The condition control power says no more, right? Unless the count here reaches 3. That triggers transition 3. Okay. Now in RDT of TCP, this event is going to also trigger fast retransmission. So in a way, when there's dupe act count equaling 3, then we do something for the condition control and then some more for the reliable data transfer. Now in the condition control, what we do is setting the SS thresh to half the window size, and window size to half of the current window size, which is now the value of SS thresh. And then reset the duplicate act count, right? And then we can begin doing the RDT, which is to fast retransmit packets. Now the number of packets we can send now then is determined by the condition window size we just set aside earlier. Transition 4, this is also packet loss, but this is packet loss detected by having a timeout. So in this case, the condition control says we need to set SS thresh to half of the window size, and the window size all the way down to 1 packet, and then reset the dupe act count. And then from here, the RDT mechanism, which is what to retransmit the missing segment. And because this time, in this case, condition window is set to 1 packet, therefore we only retransmit 1 segment. Okay, no matter how it is, how many packets have been sent, how many yellow packets or yellow bytes are there in the sliding window.
All right, so that was slow start. Next is congestion avoidance state. Recall, in slow start we do EI. In congestion avoidance we do AI. So you can imagine congestion avoidance state. Similarly to the slow start state, there are also 4 transitions. New act, dupe act, 3 duplicate timeout, 3 duplicate act, and timeout. Okay, 4 transitions. But among the 4 transitions, the new act transition will be different because in slow start, EI. In congestion avoidance, AI. So obviously the window size increment mechanism will be different. So pay attention. Right after this video, quiz 28 is coming up.
Done with the slow start state. Now let's move to the congestion avoidance state. So the first thing is, hey, when do we transition from SS to CA? Yep, when the congestion window size is larger than the SS thresh. And that takes us to the congestion avoidance state, where we see again, transition new act, transition duplicate act, transition dupe act count equal 3. And hey, where's the timeout state? Well, the timeout state is actually here, right? Because when we're in the congestion avoidance state, timeout is actually series packet loss. We reset the congestion window down to 1 end. Start from the slow start, increment the window size exponentially. Start from the slow start. So we need to do a state change in this finite state machine, going back from CA to SS. Okay. And otherwise, all these the same, just like timeout event. Similarly, for dupe act count equaling 3, all the same, Okay. Actually, similarly for dupe act, just incrementing the duplicate act count. But the last one, the new act, wow, we need to be careful here. All right, because in SS versus CA, when we receive a new act, meaning no loss, we actually increase the window size differently. So yes, this is why you see here. In SS, in SoStar, we're incrementing the window size by 1 segment per ACK. Here, we need to increase the window size by 1 segment per round trip time. So be very, very careful here. This is receiving an ACK, not, hey, checking and we see that there's 1 round trip time elapsed. So we need to figure out exactly the amount to increment to the window size so that after 1 round trip time, the increment will be exactly 1. And how do we do that? Think this. If the window size is CWND and the packet size is MSS, how many packets will be out in 1 round trip time? Yeah, this many, isn't it? Okay. And after all these packets come back in, the increment of the congestion window should be 1. That is saying we cannot be incrementing the window size by MSS. We need to increase this much. Okay. After this amount of packets received, then we add to this value. So we need to divide this value by these. That will say this is the amount we need to increment per packet. Okay. So if we rewrite this formula here, it's what? MSS multiply, so MSS multiply reverse of CWND to MSS. So after reversing, MSS at the top and then CWND at the bottom. And that is TCP congestion control sender's finite state machine in a simplistic way. You see here, let me summarize again. Yeah, so these are the events receiving new ACK. These are the events handling timeout. And these are the events handling receiving the duplicate ACKs and it's reaching the count of 3.
And that takes us to quiz 28. All right, guys. So this is for you guys to exercise, okay, the finite state machine. All right. So I'm actually showing the finite state machine already here. Okay, let me go to, the PowerPoint slide. Okay, already here. So it's easy for you to follow. And the scenario is we have host A sending data to host B. And the initial window size here is 4 MSS. And the threshold is A. All right. And given that the window size is 4 MSS, then we are allowed to send 4 packets out. And by the way, in quiz 28 and in fact 29 all the way to 31, the packet size are constant. All of them are 1 MSS bytes long. Okay. So the first packet will be carrying sequence number 0. Let's just assume that we start from 0. Okay. And packet size is MSS. Now, can you imagine the sequence number for the second packet? There you go, MSS. The third packet, 2 MSS. The fourth, 3 MSS. Very good. And you'll see that when the first packet arriving at the receiver, host B, an acknowledgement will be generated, right? It will be telling what is the next byte expected by host B. So the ACK for the first data will be exactly 1 MSS. For the second packet, 2 MSS. But in this scenario, the third packet is lost. So we're not going to get the third data. So when the fourth data packet arrives at host B, which is 3 MSS, hey, this is out of order, isn't it? I'm expecting 0 here, 1 MSS here, 2 MSS here, but I'm receiving 3 MSS. What do we do? Yeah, in TCP, we buffer 3 MSS, but we do not extract the data and pass it up yet. And we do what? Send duplicate ACK. Okay, so this one here, then will also carry 2 MSS as the acknowledgement number. Okay, now what I'm asking is when the first ACK arriving back to the sender, this time point, yeah, the window size, this is a new ACK according to the mechanism, according to the finite state machine. When we receive a new ACK, the window size will be changed. So what is the value of B here at host A? For the second ACK, this is also a new ACK. Oh, the new ACK transition will be triggered again. And then this is a duplicate ACK. Okay, so the dupe egg transition will be triggered, okay, and influences the condition window. Okay, so B, C, D are the condition windows of host A after receiving the 3 eggs coming back. Okay, so I'm asking you to derive the value of the condition window size BCD when threshold is 8 versus when threshold is 4. All right, so threshold, if A is 8 versus A equals 4, the situations are different, isn't it? Because that tells also whether you are in the slow start state or condition avoidance state. Okay, so the exact transition you trigger will be different. Now let's go to Discord. This is a W10 quiz 28 channel. Guys, we will not be taking the fast responder for wellness. This is the best time for you to exercise, whether you get the finite state machine, whether you get TCP's condition control mechanism. So you guys will have 5 minutes time to work on it. Make sure you write a derivation. Don't just tell the numbers, because you don't know if you're getting it right. Only when you write out the derivation, exactly the calculation process, then you are very sure. And by the way, if you hate typing up on the score, it's okay. You can write on your own notebook and take a photo of that and upload it, okay, to the score. I think I see a couple teams did that in the previous 2 quizzes. Okay, excellent idea. Oh, all right. So hey, let's start counting time. You guys have 4 or 5 minutes. Take your time. Make sure you get it.
Okay, very good question from Lucas. Yeah, to tell whether the TCP is still in SS or CA, you check whether the current window size is higher than the SS thresh. And if A equals 8, yeah, these 4 packets are sent in SS. And when the 3 ACKs are arriving back to host A, hey, the window size is still lower than 8, therefore still SS state. But when it's 4, when A equals 4, then situation is different, isn't it? Okay, I hope that explains, Lucas. Yeah, you see, guys, feel free to ask, because if you are confused, chances is also high that someone else is also confused. Okay. So you see that the video might go a little bit fast. You didn't capture that. So TCP connection, right from the start to the end. At the beginning, SS, later CA. To tell them apart, the transition happens, okay, when the condition window size exceeds the SS thresh. Yeah, so team 17, Tasha. Okay, you see that you showing derivation. This is great. This is perfect. Okay, let me give you more hearts. But you see, Tasha, when you show this, then I see that there's a slight confusion. There's a slight confusion. Tasha, it should be B plus 1 over B. It's not quite B plus 1 over B. The whole B plus 1 over B is different from, well, actually, you know what? You're right. You're right. Yeah. No, you're right. Perfectly right. Excuse Polly. Okay. So B is 1 plus a quarter of a packet because the size of the window is 4 packets. So you see also roughly that after receiving 4 eggs, the window size will be very close to 5. Okay. Very good. So if I may, let me draw your attention here. Okay. The case where the threshold is 8 is simple because it's in the soul star. For every egg you receive, you increment the window size by 1 packet. Okay. So Junhuan, great. Team 9, you guys are great. You are the only one who adds the unit of the numbers you're presenting. Yes, 5 packets in the window, that means 5 MSS. Okay. And so let me draw your attention here. So the first Q1 asks when SS is 8 and it's soul star. So you increment the window size by 1 MSS for every new egg. If it's dupe egg, you just do nothing and increment the dupe egg counter, and that's all, right? So the tricky case is Q2, A equals 4. In that case, we are in the congestion avoidance state. Then we actually increment the window size this way. Okay, it's MSS plus MSS over the congestion window. Okay, and so let's see. B should be this plus this. And given that the congestion window size is 4 MSS, so you just, substitute CW and D with the current value, and what do you have? Yeah, 4¼ MSS. All right. Now, some of you might be asking, do we send 1 packet, 2 packet, or more packets if the size is 4.25? Well, when this ACK arrives, that means, this packet is received all right. So we slide the window over. We definitely is guaranteed to send, we are allowed to send 1 packet, 1 MSS for sure. Now the window size is increased. Can we send another packet? Well, it depends. Okay, it depends on the definition of the implementation. So usually when this is not quite yet 1 MSS, we hold on, okay, instead of sending another packet that's in 1 MSS. Or another packet in 1/4 MSS, okay. So in most implementation, we hold on, okay. Send only 4 MSS in this case. Okay. But you can see some optimized implementation that says 1/4 of packets after this, okay. 1/4 more packet after this. 1/4 MSS packet after this. All right, so what about C? C will be the current window size plus, according to the formula. Let's substitute CWND with the current window size, which is this. Then you do the derivation, and we get this. And if you have a calculator, you'll see that this is 4.49, about 4.5, not quite 4.5. But essentially, every 4x, you get a roughly 1 MSS increment. All right. So the formula here looks weird, but it does work. Okay, you get after a round trip time, incrementing the window size by 1 MSS, by 1 packet. Okay, so let's go back to the score and see what the rest of the teams did. Okay, very good. Very good. Awesome. Great job. Great job. Ryan. One reset after timeout? Well, this duplicate just come back. Yeah, so Ryan, think about this. Because D is happening at the time the duplicate ACK is received. It's not quite yet happening at the timeout. Okay, think about this. Okay, yeah, think about it. Okay. Good that you try to think on your own and see if you can come up with the same thing. Because a lot of times if you just follow other people saying, it's very easy to get carried away. Okay, they understand it, they say it that way, but you might not really understand. Okay, so take your time. So definitely, calculation of BC, you get it right, Ryan. Okay, team 15, okay. And guys, by the way, although only one of the members type up the solutions, and I know for sure that whoever did this,
understands how the mechanism works. The other members, definitely you make sure you exercise. Okay, so this is the kind of thing that would definitely appear in the exam, and you want to have certain fluency so that when you are working on the exams, it's going to be fast. Okay, and that will save you some time to work on other problems that are more challenging, isn't it? Perfect. Lucas, there you go. There you go. Ming Huang. Hey, Team 5. Excellent job. Okay, good. Very good, guys. Okay, I'm happy to know that you guys have picked it up, except Ryan. Think about it. Good. What time is it? Oh, 11:11. Okay, guys, you know what? Perfect timing. Let's take a break. Okay, I know your brain is probably burning right now because it's not exactly intuitive doing AIMD. So let's take a break. You will have some time to think it through, Ryan. Sorry. So let's break. It's 11:11. Let's resume 11:21.
Okay, so I'm restarting a little bit earlier than 21. I hope that it's okay. Okay, so the next topic is still the finite state machine of TCP's condition control, because there's one optimization to TCP's condition control mechanism. Okay, it's called fast recovery. Okay, so pay attention to this video, guys. Definitely pay attention to this video, because right after that we have a series of quizzes coming up. Okay, number 29 all the way to 31 are about fast recovery. Okay, this one is a little bit complicated, so make sure that you focus. This finite state machine, now we walk through it. It's kind of symmetric and clean, relatively easy to track. This is also the mechanism implemented in the TCP Tahoe, the version 1. In TCP Reno, it's actually being extended. So the hack here is called the fast recovery. Okay. Now, this version looks substantially complicated, but let me tell you this, hopefully makes it a bit simpler for you. The only transitions that are actually touched from the previous finite state machine are just these. Okay, the case where the dupe at count reaches 3. So previously what we do is this. We set the SS thresh to have the window size and the window size to SS thresh. But now, okay, in Reno, we actually add 3 more segments to the window size. So we are actually a little bit more generous about setting the window size. And the logic behind this is, hey, if we receive 3 duplicate acts, that means the channel between the sender and receiver, there's enough capacity to allow 3 data segments to go. Although out of order, still triggering duplicate acts to come back, right? So 3 spaces, therefore generating 3 duplicate acts. So there's enough capacity, right? So we don't have to go all the way down, okay, or half down. So as long as, hey, we're seeing, duplicate acts, that means the capacity is still there. Maybe this is just a very, short-term condition, short-term precondition, okay, happening. So maybe we just keep, pushing a little bit more, and when this short-term outage or short-term condition goes out, then we can come back to normal. Okay, so this is the logic behind the fast recovery mechanism here. So after adding 3 more segments to the window size, we enter the fast recovery state. And staying in the fast recovery state, we apply the same logic. As long as we receive a duplicate act, we continue to increment the window size, because being able to receive a duplicate act is because we allow 1 data to go out. So this is going to be repeated until what? Until we finally get a new act back, or all these extra packets we send out by being more generous about the window size somehow get dropped in the middle, meaning the congestion is not short term. It's a bit more pathological, persistent. So we will run into timeout here. In this case, drop the window size to 1, feel free. But if it's in this case, it's okay. Then we can just, reset the window size to normal, which is half of the window size, and then go back to the congestion avoidance states, and then begin linear increase again.
All right, so you see the optimization is when you have 3 duplicate acts. In TCP's reliable data transfer, we retransmit. Okay, in TCP's condition control, we drop the window size and the threshold both to half. But with the fast recovery, we drop the threshold to half, all right. But we drop the window size also to half, but plus 3 packets. Okay, so this is to allow 3 more packets to be sent. Okay, so there's chances of having more duplicate acts coming back. In case the condition is light, we might get the data that's seemingly lost back. You see? Because we just retransmitted the packet after receiving 3 duplicate acts. See? It actually makes sense, but the mechanism, similar to how we do AIMD, looks a little bit tricky, okay, mechanic. Okay, it's a little bit hard to build the intuition. So let's go through quiz 29, 30, 31 to try to build some fluency, okay, into you reading these fast recovery or fast retransmission finite state machines. So this is quiz 29. As you can see, the scenario is continued, okay, from quiz 28. Okay, so 4 packets sent. The third one is lost.
So we only see 3 eggs back. The first 2 eggs are new egg, but this one is a duplicate egg, right? So we see B, C will be incremented because now I'm actually setting the SS thresh to 8. So this is obviously still in the slow start state. Okay. Now I'm not asking you the value of B and C now. I'm asking you, hey, so when this is incremented to 5, B is now 5. Host A here will be allowed to send 2 packets, right? One is, hey, this packet is freed, the window size over. And now the window size is incremented as well, so you're allowed to send 2. And this is the characteristic of the slow start, isn't it? For each egg, you increment the size by 1. Therefore, every time you receive an egg, you are able to send 2 packets out. So there'll be 2 packets out from egg 1 MSS. There'll be 2 more packets out from egg 2 MSS. So I'm asking you, what are the sequence numbers of these 4 data packets? And these data packets will arrive at host B. And they will generate eggs. Okay? New eggs, diff eggs, what eggs? What are the sequence numbers of the 4 eggs coming back? All right, so let's go to the score, W10, quiz 29. Guys, again, you have 5 minutes to think this through. Okay, provide reasons. Okay, provide reasons. So let's start counting time. And by the way, guys, if you look at the okay, so let me go back here. If you look at this, the timeout is set such a long value. Okay, so this scenario here is not experiencing timeout at all. Okay, so when these new data packets are sent, new eggs are coming back, they are within the timeout interval. So there's no timeout retransmission. Okay.
So you guys can probably see that bees keep saying, hey, I need packet 2, I need packet 2. It's a little bit annoying for Jose, isn't it? Yeah. So to build some intuition, host be sending duplicate X. It's just like human being asking, hey, when are you going to turn this in? When are you going to turn this in? Yeah. 2, yeah. Packet 2 is being requested again and again and again and again. All right, so I can see. So far, so good. So far, so good. Okay, Tasha, you've got it right as well. Ryan, very good. Ali? Very good. Oops. Someone just type up a solution. There. All right, great. Very good. Now, let's go down the quiz. So these are quizzes back to back. All right, so and one after another. So this is a quiz 30. You see the scenario remain the same. Okay, and we know the sequence number for these 4 data packets. We know the sequence number for these 4 eggs. Okay, now, guys, this one is the first egg that says I am 2MSS. This is the first duplicate egg 2MSS. And you know what? This is the second one. And this is the third one. So I'm asking, at the time we receive the 3 duplicate eggs, okay, what do we do with the threshold? And what do we do with the condition window size? Okay, and if you pay attention to the video earlier, the value will be different depending on whether there's fast recovery or not. So Q1 asks, if there's no fast recovery, what will be the value of E and F? If there's fast recovery, the value of E and F might be different. All right, guys, let's go to channel W10. Quiz 30. We have an answer already. Good for you, Yuting. You are following this very fast. Good. So I guess you are one of those who are more math aptitude oriented. So guys, come over here. Tell me, what
the value of E and F are without fast recovery versus with fast recovery. Okay, so we also have 5 minutes time here. Yeah, so I guess it's not exactly that hard, right? Previously, we drop SS thresh and window size both to half of the current window size. And the current window size is D divided by D, and the value of D is 6. So 6 divided by 2, 3. But with fast recovery, right? So the threshold is dropped to half the window size. This is the same. But the condition window size is SS thresh plus 3. So 3 and 6 in the second case. All right? Good. Not that challenging. I can feel. Now, we'll go down to the last of the series. The last quiz of the series. This is quiz 31. All right, so now, hey, this is the moment where we receive 3 duplicate egg, right? Any packet sent at the 3 duplicate eggs? If yes, what is the sequence number? Okay, if this is without recovery, Okay, any packet sent here, and what is the sequence number? If this is with fast recovery, any packet sent, and what is the sequence number? Okay, so let's go to, again, the discourse space, channel 10, W10, quiz 31. Okay, for this, how about we set it to a lower time interval, say 4 minutes, okay? By now, it should not be that hard. Yeah, yeah, guys, you guys are right, right? Because both without fast recovery or with fast recovery, after receiving 3 duplicate eggs, we retransmit the missing segment. Even though with fast recovery, adding the condition window size to half plus 3. Okay, now let me just check this one real quick and go back here. Guys, okay, there's a quiz 31.5. Can anyone tell me, okay, when this duplicate egg arrives at host A, would there be a packet triggered without fast recovery versus with fast recovery? Okay, if you know the answer for that, type it up on the chat or go to Discord in the Ask Us Anything or random channel, type up what you think. Okay, when we receive this duplicate egg, is there a packet sent in TCP's condition control without faster recovery versus with fast recovery. Okay, so that is a bonus opportunity. Okay, good. All right. Hey guys, hey, there's no shame in learning. Guys, no shame in learning. When you are under 30, no shame making mistakes. And a lot of times it's better to admit the mistakes than admitting mistakes. Okay, good, very good. So you see, TCP's condition control mechanism, without the quizzes, it would be really fuzzy and complicated. Now with the quizzes, okay, I hope that you get a better idea, okay, how they work, how the mechanism works. Good, I think we are ready to move on, okay? And we'll start talking about all the other additional topics regarding TCP's condition control. First is modeling. So this topic is special because nowadays internet is huge, and there are places where we have companies that are very resourceful, so they can actually build really thick pipes, okay, high capacity links between their servers to their other servers in another country. Okay, so you have big thick pipes and long distance, and they want to be able to back up data from one data center to another data center in another country. You know what? In that case, TCP as it is now is too slow. Okay, so this topics analyze TCP's throughput, the average throughput, and tells that the TCP without change is not going to work for long distance high volume transfer. Let's cover two more topics related to TCP, and these are about what the research community is doing trying to improve TCP for the future need. First is about how one improves TCP such that it can support long, fat pipe. Okay, what I meant by long pipe is a TCP connection that has long round trip time, and a fat pipe is that it has high throughput. Okay, and this is what we know. Okay, the sending rate or the throughput should equal the window size divided by round trip time. So this is 0.1 second, and the rate should be 10 gigabits per second. So you see the congestion window is essentially the two terms multiply, and that is 1 gigabits and approximately 110 megabyte. So at the sender side, receiver side, 100 megabyte is required to buffer the packets that are in flight. And this is just to maintain one connection, right? If you have 10 connections, that's already 1 gigabyte of memory. If you have 100 connections, that's gonna probably take all your memory away. This is just one issue. Another issue is this. TCP is actually go back and like. What if you run into a packet loss that is triggered by having 3 duplicate acts? What we do there is we set the window size to half of the window size before a loss event is detected. And you know what? The window size, the number of packets there could be, can be as high as this, because if we divide this by 1500 byte, you get these many packets in flight. So in that case, we'll have to retransmit all the unacted packets, okay, and half of the window size here, okay? So that's, 41 and 666 something packets that we need to send. The bandwidth consumption there, right? The amount of bandwidth we might be wasting there is very significant. So TCP, the current design, isn't really ideal to support long fat pipes. And this is actually assuming that there's no packet loss at all, no bit error at all. What if we have error? One will have to derive the TCP throughput model considering loss before one can see how big a problem it is to try to support long fat pipes. So let's try to do some derivation here and see if we can come up with the average TCP throughput, okay, provided the window size, round trip time. The assumption is that let's ignore the slow start, okay? Consider just the congestion avoidance operation and assume that there's always data coming in. And the scenario is very simplistic, which is illustrated here. Our over time, the changes of the window size is exactly from half of W increase all the way to W, and W is where the loss will always occur, and therefore we drop the window size back down to half W because this is in congestion avoidance. When there's a loss, drop to half W. When there's a loss at W, drop to half W. And so it's not hard for you to see what is the average window size? Yeah, the midpoint here, right? So 3/4 of W. And therefore the throughput is what? The average window size divided by the round trip time, which is this term here. Now, if we plug in, yeah, this is the goal throughput, and this is the round trip delay. Now, what is the window size now? Well, it will be this term multiplying each other and multiplying the reverse of 3/4. Therefore, it's 4/3 now. So this is actually even bigger than the CWND we're calculating there. So with loss, yeah, the amount of memory required to store data higher, the amount of unnecessary retransmission also higher. We can go on and on, right? Try to derive a more general model. So let me not go over the exact derivation, just tell you, if the loss probability is L, okay, one can actually come up with the TCP throughput being represented this way. Round trip time here, okay, square root of L here, and the maximum segment size here. Okay. Now, if, take the same example here, take the same setting there. Packet size being 1500 bytes, round trip time being 100 milliseconds, and the goal throughput 10 gigabits per second. In order to achieve so, the loss rate needs to be as slow as this. 2 multiply 10 to the power of -10. Okay? Now this is a loss rate that's also impossible pretty much on the internet today. All right? So definitely we need new versions of TCP to support very high fat pipes going a long way.
All right, so that was what TCP modeling is for. Okay, and there are people working on special versions of TCP specifically for the long, thick pipes. And next topic is TCP fairness. Okay, recall in the transport layer we have two protocols. One is UDP, the other is TCP. Okay, TCP to TCP flows, you will see in the video that hey, the TCP flows will be fair to each other eventually, no matter what the beginning state is. When they are long enough, they would approach fair bandwidth. But when TCP flows are running with UDP flows, where UDP doesn't have congestion control at all, it's an issue because UDP, one can actually use the UDP connection to send very high bandwidth streams. For example, videos prefer sending through UDP. Okay, so this video talks about intra-TCP flow fairness and inter-TCP UDP flow fairness.
Another major issue is this, fairness. Okay, let's talk about fairness at this level first, the TCP fairness. Okay, so what we're talking about here, the goal is to make sure that the K TCP sessions will share the same amount of bandwidth if it go across the same link of bandwidth R. So the eventual share of the sending rate or the throughput should be R divided by K. Okay, so in this scenario, what you're seeing is the router in the middle, the capacity is R, and we have two connections. So connection 1 here should have half of R, and connection 2 here should have the equal amount. So we have two competing TCP sessions, and they're competing for a link with capacity R. So what I'm showing here are the relationship of connection 1 and connection 2's throughput. So one extreme is connection 1 gets the whole R, while connection 2 gets nothing. And this is the other extreme. Connection 2 gets R, while connection 1 gets nothing. The fair point is right here in the middle. Okay, each of them gets half of R. So you see here, the dotted block line is to draw the equal bandwidth share, meaning if the bandwidth of connection 1 and 2 falls on this black line, yeah, they'll be fair to each other. Now, the blue line here is actually illustrating, this is actually the boundary, the capacity of the link. Okay? If the sum of connection 1 and 2 throughput goes beyond the blue line, that means congestion is beginning to occur, packets will begin to drop. Now let's say we start from here. Connection 1 having this much throughput, while connection 2 have, very small throughput. As time goes by, okay, we're in congestion avoidance state, so we will continue to do additive increase. Therefore, connection 1's throughput will continue to increase, just like connection 2's throughput will continue to increase. And the characteristic, the value of connection 1 and 2's throughput will fall along this line here with the slope of 1. Now, as it goes beyond the blue line here, this is actually beyond the network capacity, we'll begin to see packet drop. And what we'll see next is what? The two of them reducing the throughput to half of the value here. Okay, so this is connection 2's. Connection 2's throughput drop to half of it. Okay, right down here. Connection 1's throughput drop to half of it, right down here. Okay. So having a loss, decrease the window size by a factor of 2, and that takes us from here down to here. So this is the current throughput of connection 1 and connection 2. Let's move on, right? It will continue to go additive increase as we are in the congestion avoidance state. Crossing the boundary of blue line, drop packet again, and decrease the window size again. Okay, again by factor of 2. So we go down here. So you see, additive increase, multiplicative decrease. Additive increase. You see, the throughput of connection 1 and 2 are actually what? Approaching the equal bandwidth share. So TCP between the connections, the mechanism warrants that they will be fair to each other. So we see between TCP connections, they'll be fair to each other. But what about TCP to UDP? Multimedia applications actually prefer not to use TCP because TCP has this window size mechanism when there's congestion drop it, right? So the rate, sending rate is actually throttled by the congestion control mechanism. So some of the multimedia applications would prefer UDP, and they would send audio video data at high rate, constant rate, without really, adapting to congestion. So would that be fair? Of course not. Okay. And not to mention this, what if you have applications who open up multiple parallel TCP connections, okay, versus other applications who opens one TCP connection at a time to send data? Now consider this case. A link of rate R with 9 existing connections already, right? Then each have R over 9 share of the bandwidth. When there's a new app coming in asking for 1 TCP, that app then, right, will share with 9 existing connections and each get 1/10 of the R. But if the new app comes in and then asks for 9 parallel TCP connections, so that will be what? R dividing by 9 plus 9. And each connection is this much because the new app gets 9 of these, so let's multiply this by 9. New app gets half of R. So a new app designing this way versus a new app designing this way, okay, competing with other existing connections, it's actually hard to make it fair. And you know what? Web browsers these days do this. Okay? They might start parallel connections to fetch one page. Previously, Internet Explorer were very aggressive. Okay? For example, starting 8 parallel connections, 4 parallel connections to try to fetch web objects in a page. But nowadays, the HTTP consortium actually regulates so that they do not overdo this.
All right, so that was fairness. It's always a topic that is very sensitive. So even though we can try to keep intra-TCP fairness, and we can try to regulate UDP a little bit so that it works like it's friendly to TCP. But at the application level, one can exploit, having multiple TCP connections opening and downloading just one object at a time. So then you still see unfairness at that level. Okay, so it's very easy for someone to come up with something to exploit so that it creates an unfair situation. All right. So let's not touch the fairness topic even further because again, it's a sensitive topic. And let's work on quiz 32.
You see from the video, AIMD avoids congestion, right? So that's what TCP's congestion window adaptation mechanism works in the congestion avoidance state. So you see that the mechanism achieves that purpose. But you know what? You just heard something. AIMD also achieves intra-TCP flow fairness. Okay, so AIMD is nice, avoids congestion, and make the TCP flow fair to each other. Okay, now let me ask, are there other ways of adjusting CWNDs at the congestion window size such that it will be fair? Meaning converging to the equal bandwidth share. Would the connection's throughputs converge to equal bandwidth share if CWND adapts differently? Yes or no if CWND adapts in an AIAD fashion? Yes or no if it's MIMD? Yes or no if it's MIAD? So that is quiz 32. Let's go to the score. Oh, okay, Ali. No, okay. Channel W10, quiz 32. You know what? You guys have only 4 minutes to work on this. Okay. Ali, why? Why no? Okay. I have to say that, Ali, you're correct. But why? Okay. Exactly. So MIAD is the worst, right? It's gonna create unfairness. You know what? If you think about the household incomes in a country recently, especially for the capitalism countries, riches get richer, poor get poor. AIMD as how usually fortune accumulates as well. Ouch. Yeah, again, fairness is a sensitive topic. Okay. No, I see. And Team 7, very good. Thank you for providing why you see that MIAD is not good. It's going to make things worse. Yes, indeed. Okay, yeah. So the rest of the teams, I know you guys want to talk about it. Can anyone tell me why AIAD MIMD doesn't work? Team 2 here. No, as the ratio of increase and decrease are both the same. Yeah. So essentially, so AIAD will be this. Okay, initial state being here. AI goes here. AD compacts here. AIAD. Are they approaching? Are the two connections approaching the equal bandwidth shear state? MIMD, let's see, same reason, exactly. MIMD means, okay, throughput double here, and you know what? They would just go also quickly out of the space, but in parallel with the equal bandwidth share. Continue to be unfair as long as the initial state is unfair. So AIAD, MIMD, only one exception that they will be fair, only when the two connections at the beginning are fair to each other already. Good. MIAD, let's see, if they are fair at the beginning, yeah, I think they will stay fair too. Yeah. Okay, very good. Bonus to team 2. Very good. All right, so guys, that's the second topic. We do have one more topic, which is this really weird version of network-assisted condition control mechanism implemented in TCP, but never get deployed. It's called the ECN mechanism. But you know what, guys? The amount of time we have remaining, you know what? Let's just play this video. It's 3.5 minutes. We have just enough time to play this. Okay. That was TCP, taking the end-to-end approach. Let me introduce another mechanism that's called the ECN. It's also defined for TCP/IP for the internet, but it's not really implemented or activated. And it's taking the opposite approach, the network-assisted approach. The ECN mechanism works this way. First of all, in the IP packet header, okay, or network layer header, there's this special field called TOS that stands for type of service. So in that field, 2 of the bits are assigned for the purpose. They are also called the ECN bits. Okay, so I'm using a green packet here to indicate that that packet header, especially the network layer header, is carrying the ECN bits. They were initialized to 0, that means no congestion, but as the packet travels through the network, running into a busy router like this, the bits will be turned down. And the packet will eventually come, okay, and arrive at the receiver of the data. And the network layer here at the receiver is going to see, oh, these 2 bits are turned on, therefore notifying the transport layer. And at that point, okay, the transport layer of the receiver is going to do this. Receiver is going to set the ECE bit on the packet, going back to the data source, like this. Okay, so it's going to be in the ACK packet, and the ECE bit being turned on. So this is also called the E flag, okay, in the TCP packet field. Sender there, upon receiving this ECE bit packet, will then send a packet that is then the data packet going back to the receiver. And that packet is a little bit special because there's also a special bit being turned on, the CWR bit. So this is congestion window reduced bit. This is so that the destination here, the receiver of the data here knows that, okay, so my notification here, you indeed received it and reduced the sending rate. Okay, so therefore the receiver of the data does not need to send ECE bit again. Okay, otherwise, the source is going to reduce sending rate again and again. Right? And the E bit and the C bit, the E flag and the C flag are in fact, again, in the TCP packet header. Okay, so along with all these other flags for TCP. And that finally takes us to the summary of the chapter 3. We went through the basic functionalities of transport layer protocols, multiplexing, demultiplexing, reliable data transfer, flow control, and just now, congestion control. And we talk about how UDP and TCP implement these services. Particularly, we spend quite a lot of time here, as well as here. We are now finally ready to leave the network edge. So departing from the transport layer and down to the network layer and into the network core. But the network layer is going to be split into 2 chapters. Chapter 4 is going to be about the data plane, how we forward packets real fast. And chapter 5 is going to be the data plane. So how do we control these paths we select such that the packet will travel and eventually reaching the destination, reaching the receiver. All right, so that was the ECN mechanism. So you see that there's additional action exchange between the network layer and the transport layer. And this is the reason that this one, although you guys prefer the network assisted approach to congestion control, but it never get deployed. And Lucas asked, why do we need 2 bits for the ECN flag? You know what? This is a very good question. So having more bits allow you to indicate the urgentness or the degree of congestion or the shortage of buffer space, free buffer space, a little bit better. Okay, but you know what? In the spec of ECN, it was never clear. Okay, in fact, that slide provided by the textbook authors was a little bit mistaken in terms of setting the 2 bits. Okay, so so I'm just giving you a simplified example of how these ECN flags can be used. Okay, I hope that explains. Okay, Lucas. All right, guys, that's all the time we have, and next week we'll start fresh and begin talking about the network layer. That is chapter 4. Okay, so next Tuesday, chapter 4, and next Wednesday, exam number 2. With that say, I say goodbye. Okay, enjoy the rest of the week, and hope that you don't get this dizziness, dizziness from the aftershakes, okay, of the major earthquake. Okay, so bye. Yeah, Ryan, bye. Aslam, Ali, Ja. Hey, international students, sorry, I don't know. It will be a very interesting experience for you, okay? So living under heavy quake situations like yesterday. Yeah, so yesterday I have no idea whether it's me or the earth is shaking. I guess it's probably the same for you guys. Okay, bye. Yeah, I just hope that situation eases out gradually instead of having another major one coming. Okay. Hey, in any case, hanging there. Still thinking. Oh. Cassandra, yeah, take your time. And it's okay. A lot of times, Polly doesn't get answers for some of the problems necessarily. Yeah, so Cassandra, take your time. Okay. Great job, guys. Great job, guys. All right, bye guys. Yeah, bye Matthew, bye Cheng'en, bye. And Tingshen. Hanjin, you're great. You're great. Okay, your solution for the MIMD is finally the correct one. Team 8 as well. Okay, Team 8. Perfect. Thank you, Hanjin. Okay, bring that moment for Polly as well. All right, that's all for this week.